Welcome back to the explainer. So, picture this. You're staring at a technical interview screen. It's a complex tree or a massive 2D grid, and you just completely freeze. If that sounds familiar, you are not alone. Actually, over 70% of candidates totally freeze up on grid questions. It feels like this impossible, twisting maze, right? Well, what if I told you there's a master key? Today, we're unlocking the secrets of depth-first search, DFS, and backtracking. This is literally your ultimate tool for navigating complex data structures with absolute confidence.
Because here is the absolute golden rule of technical interviews. Patterns beat memorization. I mean, trying to memorize the solutions to 50, 100, or like 500 individual LeetCode problems. It's impossible. And honestly, it's a massive waste of your time. Instead, mastering the underlying templates of recursion and backtracking, now that is what actually equips you to solve problems you've literally never seen before. Once you have this master key, the whole maze just makes sense.
Okay, let's dive into our roadmap for today. We'll be hitting 5 main stops: demystifying DFS, the backtracking blueprint, matrix mazes and islands, optimizing the search, and finally, mastering the pattern.
So, let's kick things off with Section 1, demystifying DFS and binary tree traversals. You see, before we can sprint through complex combinatorics, we really have to know how to just walk through a basic tree.
Think of depth-first search like walking into an actual, physical maze. You wouldn't just check every single fork in the road one tiny step at a time, right? Instead, you'd pick a path and you'd walk as far down that path as you possibly can. You keep going deeper, deeper, deeper until, bam, you hit a dead end. When you do, you just retreat or backtrack to the last fork and try the next path. And honestly, that's DFS in a nutshell. You go as deep as possible before retreating.
And here's the cool part. Despite how crazy complex tree problems can look, all DFS tree traversal fundamentally boils down to just 6 variations. That's it. You've got your standard, pre-order, in-order, and post-order, and then just their reverse counterparts. Whether you're validating a binary search tree using an in-order traversal or finding the lowest common ancestor with a post-order traversal, these are the ground rules. This right here is your foundation.
Now, when you actually go to code these traversals, you face a big choice: recursion or iteration. Recursion is just incredibly elegant. Think about the binary tree in-order traversal problem. You can write a recursive solution in just a few lines of really concise code, mainly because it implicitly uses the system's own call stack. Iteration, on the flip side, forces you to manually manage an explicit stack data structure. Yeah, it's a bit more code, but it gives you this highly granular, absolute control over the memory and the process.
And speaking of memory, take a look at this number, 10 to the power of 4, 10,000. When you read the constraints of a binary tree problem, you are going to see this a lot as the maximum number of nodes. So why does this matter? Well, if your recursive call stack goes 10,000 levels deep on a heavily skewed tree, you might just hit a Stack Overflow error and literally watch your interview hopes crash right along with your program. So understanding your traversal complexity, both time and space, is absolutely critical before you write a single line of code.
All right, moving on to Section 2, the backtracking blueprint. This is where we shift gears from simply traversing existing nodes to generating entirely new combinations.
Okay, so here is your universal backtracking algorithm. Think about a problem like palindrome partitioning. You don't just magically find the answer, you have to build it incrementally. Step 1, choose a potential candidate, like, say, a substring. Step 2, constrain it, as in, ask yourself, is this substring actually a palindrome? Step 3, check your goal. Have you reached the end of the string? If yes, awesome, save the path. If no, you explore further. And if that hits a dead end, you backtrack and try the next candidate. It's a remarkably simple, actionable checklist.
To really grasp the intuition behind this kind of recursive generation, think about the letter combinations of a phone number problem. If you need to find all letter combinations for the digits 2, 3, don't panic. Just break it down. Solving the 1-digit case is trivial. You literally just map 2 to A, B, C. Then, to solve the 2-digit case, you just solve that 1-digit case again for each of those starting letters. You see, you're constantly breaking complex combinatorics down into trivial, bite-sized base cases.
But you got to be careful here. Identifying your problem type immediately dictates your performance bounds. I mean, a simple tree traversal is linear. O of n, not bad. But step into combinations and boom, you're at O of n times 2 to the end. And permutations? O of n times n factorial. No way around it, that cost is incredibly steep, which is exactly why mapping the right complexity to the problem right from the jump is totally non-negotiable.
Let's pivot to Section 3,
matrix mazes and islands. Now we're going to take that DFS pattern we just built and unleash it on 2D grid problems.
So when you get dropped into a 2D grid, like in the classic max area of island problem, you aren't strictly flowing downward like you're doing a tree. You can move up, down, left, right, wherever. And if you aren't super careful, your DFS engine will just bounce back and forth forever between two cells. To prevent these nasty infinite loops, you've got to do one of two things. You either maintain a separate visited set, or, if you want to save memory, you dynamically mutate the grid itself. Just flip a visited land cell from a 1 to a 0 so your algorithm knows, hey, never step there again.
Which brings us perfectly to Section 4, Optimizing the Search. This is all about handling massive inputs to make sure your code actually runs fast enough to pass the tests. Because I have to ask you, what happens when our inputs get truly massive? What happens when that n factorial complexity meets a string that is, say, 20 characters long? I'll tell you, your standard DFS will time out. It'll just crash and burn. We desperately need to introduce algorithmic optimization.
Let's consider the word break 2 problem. A brute force DFS generation here is going to run in an absolutely abysmal O of n times 2 to the n. But by introducing dynamic programming, specifically memoization, we can drop that all the way down to O of n. How? Well, simply by caching our previously computed paths in a dictionary. Think about it. If we've already figured out the valid sentences for the substring dog, we don't calculate it again, we just look it up. It is a massive performance leap for virtually no extra effort.
And when we're dealing with dictionary lookups on a 2D board, like in Word Search 2, we need the ultimate optimization tool, the trie, or a prefix tree. Instead of checking a hash set at every single tiny step, a trie lets us know instantly if the path we're walking down even has the potential to form a valid word. If the prefix isn't in the trie, bam, we kill the DFS branch immediately. This drastically reduces our exploration space.
So let's see how this builds into an elite solution. If you want to elevate your candidate profile from the bottom 5% to the top 5% of submissions, you got to use these 3 advanced trie optimization tricks. First, traverse the tries simultaneously with your board backtracking. Second, once you match a word, prune that leaf node from the trie so you never search for it again. And third, completely remove matched words from the trie to continually shrink your search space. Guys, this is exactly how you write production-grade algorithms.
Finally, we arrive at Section 5, Mastering the Pattern. It's time to bring it all together into the ultimate framework.
Here it is, your ultimate step-by-step framework to approach literally any recursive or backtracking interview question. Ready? First, check the constraints so you know your big O limits. Second, map the problem to one of those core traversal patterns we talked about. Third, always build your trivial base case first. Fourth, write the logic to traverse the recursive branches. And finally, use memoization or a trie to optimize the bottlenecks. If you follow these exact steps, you're no longer just guessing. You are engineering a solid solution.
So I want to leave you with this final provocative thought. When you sit down for your next technical interview, are you going to try to rely on brute force memorization of 1,000 different maze paths, or will you master the key? Because as we've seen throughout this explainer, frameworks beat memorization every single time. Take this key, go practice these patterns, and completely crush those interviews. Keep learning, stay focused, and we will catch you in the next explainer.